Consider the points A, B, and C. They're all listed below. Which, if any, of these points are on the line y equals negative 1/3 x plus 8. Of course, in order for a point to be on a line, that point would have to make the equation of the line true. So what I'm going to do is I'm going to test 3 different points and see if they make the equation y equals negative 1/3 x plus 8 true. To do this, I'm going to write kind of a little vertical line here. And I'm going to put a question mark because I'm not sure if it's true or not. But you can see for each one of these points, I have an x and I have a y. Right? All of them have an x and a y. Let me do this one in red, an x and a y. And I'll do this last one in green. There's an x and a y. And for each case, what I'm going to do is I'm going to take the y value and place it in where y is, and I'm going to take the x value and place it in where x is in the equation and see if it makes it true. So for the first one, right, it says that y is 9, so I'm going to place a 9 on this side. And the other side, I'm going to look at negative 1/3 times x, which is negative 3, and then I'm going to add 8 to it. So I'm doing exactly what the equation says. Let's evaluate the right-hand side there. Negative 1/3 times negative 3 is a positive 1, and 1 plus 8 is 9. So because these are both the same number, A is on the line. Negative 3, 9 is on the line. For B, same thing. We're going to look at a point right here. For B, y is 6, so I'm going to write a 6 on this side. And the other side, I'm going to have a negative 1/3. X is 6 also, and then plus 8. Negative 1/3 times 6 is a negative 2, and negative 2 plus 8 is 6. So in both cases, because 6 is equal to 6, B is also on that line. The final one here, and I think I have just enough room for it, is the green one. And on the green one, we have that y is negative 3 and x is 15. So I've got a negative 1/3 times a 15 plus an 8. Plus negative 1/3 times 15 is negative 5. And negative 5 plus 8 is positive 3. And unfortunately, on the other side, we had a negative 3. So because negative 3 and positive 3 are not equal to each other, point C is not on this line. So C is not on the line. Solve the equation. It's a system of equations, rather, using any technique. This is clearly set up, I think, for substitution. I'm fond of elimination, so sometimes I find it difficult to use substitution. But you can see because they list that y is equal to negative x plus 8, I'm going to take that value of y and I'm going to replace it. I'm going to replace that in for the y in the first equation. So if I rewrite that first equation with this substitution, it becomes negative 2 times x plus 8 times y. Playing the part of y is negative x plus an 8. And that equals the number 24. So that's my substitution. And now it's just a matter of being careful with arithmetic and simplifying the left-hand side. Using the distributive property, right, we still have the negative 2x, but then it becomes minus 8x, and then plus 64. On the other side, that equals 24. If I combine these like terms, I've got negative 10x plus 64 equals 24. And now we're going to subtract 64 from both sides. And if I have the 24 and I take away 64 from it, right, I know that it's going to be a negative number. So I'm just going to take 64 minus 24, and you can see that I get a 40. So this is negative 10x equals negative 40. And when I divide both sides by negative 10, we get that x equals positive 4. So there's part of our solution. X is positive 4. And you can see we've got underlined in green right here a perfect way to get y. This tells me that y will equal the opposite of what x was. X was the number 4. and then plus 8. And when I add -4 and 8, I get that y is also 4. So my solution is x is, as an ordered pair I should write it, x is 4 and y is 4. Mr. Good has 14 coins in a jar. The coins are either nickels or quarters. If the value of the coins is $2.90, how many nickels and how many quarters are in the jar? So probably not much of a surprise. I'm going to let n be the number of nickels, and I'm going to let q be the number of quarters. And when I say that, there's a distinction between the value of the nickels I have and the number of nickels I have. So for example, if I have 2 nickels, that has a value of 10 cents. If I have 3 quarters, there's 3 of them, but they have a value of 75 cents. So I'm being real clear here, the nickels, n is the number of nickels and q is the number of quarters. Now we're told that in the jar there's a total of 14 coins. So if we're just counting them, right, if I take the number of nickels that I have plus the number of quarters that I have, I get that there are 14 coins in the jar. The other equation I have comes from their value. The value of the nickels that I have is a function of nickels times 5 cents. So if you think about it, if I have 2 nickels in the jar, their value is 10 cents. If I have 5 nickels in the jar, 5 times 5 is 25 cents. So what I write here is I write that each nickel is 5 cents, right? And if I have n nickels, 0.05 n is what those coins are worth. So if there's 10 of them, I have 50 cents in nickels, for example. If there's 20 of them, I have $1 in nickels. Plus, my quarters are worth 25 cents each, so I write 0.25 q. So what I have here is the value of my nickels plus the value of my quarters equals the value of $2.90. So here's my system of equations and lots of good ways to tackle it. I'm going to choose to take the second equation and multiply through by 100 just so I can get rid of these decimals. And it won't change much, just it'll look a little bit cleaner, I think, visually. So this is going to become 5n plus 25q equals 290. The other equation, if we went ahead and multiplied that equation through by the number -5, it would be very convenient for elimination because my n's would then be opposites of each other. So I'm going to go ahead and carefully multiply each of one of these numbers by the number -5. When I do that, we get -5n minus 25q. I'm sorry, no, minus 5q. I'm multiplying by 5. And then the last one on the other side, when I multiply -5 times 14, I get -70. So these are now complete. The n's are opposites of each other. So we're going to choose to add these equations. Equal things plus equal things is going to yield equal things. On the left-hand side, you can see the value of n's is nothing, right? -5n plus 5n is 0 n's, so I write nothing. -5q plus 25q is 20q. I have 20q. And on the other side, -70 plus 290 is positive 220. So when I divide both sides by 20, I get that q, the number of quarters I have, is going to equal 11. 220 divided by 20 is 11. Well, now that I know that, because the coins have to add up to 14 coins in total, that means that I have to have 3 nickels. So just real quick, I can write below that n equals 3, and the reason is because n plus 11 quarters has to equal 14, so clearly n is going to be 3. So my solution is I have exactly 3 nickels, 3 of these things, and I have exactly 11 quarters. Solve each of the following equations for x. Clearly show all of your work and circle your answer. In this first one, I'm going to choose to multiply both sides of that by 2x. And when I do that, it's going to have the very beneficial effect of eliminating all the fractions that I see, right? This 2x will be gone and that 2 will be gone. So real carefully, when I multiply the first term on my left-hand side by 2x, I just get simply a 7. And then when I multiply 3/2 times 2x, I get plus 3x. And then finally on the other side, when I multiply 3.25 times 2x, I'm going to get 6.5x. So this equals 6.5x. So if I subtract 3x from both sides, I get that 7 is equal to 3.5x. And if I divide both sides by 3.5, 7 divided by 3.5, that goes into 3.5 goes into 7 twice. So that means that x is 2. So for my first equation, x is 2, and I was having fun actually checking these with the calculator. It's pretty easy to plug that value in and verify that you get exactly what you're supposed to. And I encourage you to do that either manually or using your calculator. Let's try and do B on this slide, and we might have to do C on the next page. B, I'm going to go ahead and multiply both sides of this by 6. And that will have the very beneficial effect of eliminating the 2 from my first term, right? So it won't be 5/2 x, it'll just be 6 divided by 2 is 3. It'll actually be 15 x's. So let's go ahead and do that, right? So when I multiply the 6 times 5/2 x, that's going to become 3 times 5 is 15x. And when I multiply 6 times -1/3, it's going to become a -2. And then finally, 6 times 13 is the number 78. So if I add 2 to both sides, we get 15x is equal to 80. And dividing both sides by 2, I get that x is equal to, you can write it this way, right? It's 80/15, which is equivalent to, I think 16/3. Both of those are divisible by 5. And if you choose to, you can write it also as 5 and 1/3. So any of those would be fine expressions. Of course, my preference is the fraction in simplest terms, right? 16/3 is my preference. I think we have enough room to do the last one on this page, so let's see if we can do that. I'm going to multiply both sides of this equation by, maybe you have it, maybe you don't, but I'm going to multiply both sides by 8x. Did you guess that? Did you see it coming? 8x, because that'll eliminate the fractions. When I multiply 5 over x times 8x, I get the number 40. So this equation is going to become 40. And then -2 times 8x is going to be a -16x. And -11/8 times 8x is going to equal -11x. And if I add 16 x's to both sides, I think that's probably the best way to go. I get that 40 equals positive 5x, and therefore when I divide both sides by 5, I get that x will equal the number 8. So my three solutions are 8 for C, B was 16/3, and A was x equals 2. I had a definition for this arithmetic sequence, 15, 18, 21, 24, in quote first term form. I'm gonna start by just writing it down. It appears to be linear because each time I'm increasing by 3, or we would call that an arithmetic sequence. So because each time it's a plus 3, 21 plus 3 is 24. My equation would be, if I was to write it, would be 3x plus 15, right? This is my starting value, 15. And each time I'm increasing by 3. Now, if I want to write this in first term form, and let's talk about the difference again, right? Right now, if I was to plug in a 1 into this function, right, if I was to plug in that x is 1, I would get the number 18 out of it. But clearly, this is great sadness because 18 is the second term, and we want to write this in first term form. So what I need to do is just this small minor adjustment, right? And it looks like this: 3 times n minus 1, and then plus the value 15. So now, by just replacing x with n minus 1, when I plug 1 in to get the first term, you can see that this thing just behaves like the number 0, because it is. And 0 plus 15 is 15. And then from that point on, right, when n is 2, the second term, 2 minus 1 is 1, times 3 is 3, plus 15 is 18. So that small little adjustment, right, just moving from 3x to n minus 1 is how I switch it into first term form. The second part of this question says, what is the 30th term of this sequence? Well, this is super convenient, right, because this is just going to be 3 times the quantity of 30 minus 1 plus 15. So we're looking at 3 times 29 plus the number 15. 3 times 29, I actually have no idea what that is. Well, it's 3 times 30 is 90, and I take away 3. 90 take away 3 would be 87. So I've got 87 plus the number 15. So if I add these two, 87 and 15, that's 12. I believe I get 102. So the 30th term in that sequence would be the number 102. This next question is similar to the previous one. It's asking me to find the following write the following sequence in, quote, first term form. When I go from the first value to the second, I could think about it as adding 30, right? 15 plus 30 is 45. But I run into problems when I try to go to the next step, because 30 plus 45 would be 75, and I need to get a value of 135. So this is not arithmetic, right? I'm not adding the same thing each time, adding a constant value. What I am doing is I'm multiplying by 3. And it would be a smart thing to check that out with all the values, but sure enough, 15 times 45 is 3, 45 times 3 is 135, and 135 times 3 is 405. So this is a geometric sequence, and my common ratio is the number 3. Well, if I was going to write that as an equation, it would be y equals a times b to the x, where, of course, a is my first value, right, 15, and my b is the common ratio. For this one, it's 3. Now, this is not first term form, is it? No, because if I plug in a 1, I end up getting the number 45 out of it. And when I plug the 0 in, I would get 15. So again, it's the same adjustment we made with our arithmetic sequence. To write it as first term form, I'll just say the nth value in this sequence will equal 15 times 3 raised to the n minus 1 power. So this is just using a little bit different notation, but now when I plug in n is 1, I do get 15 out of it. 2 would give me 45, 3, 135, and 4 would give me 405. A line has intercepts at 0, 6, and 2, 0. So I've got the y-intercept there and followed by the x-intercept. It says find the equation of this line. Well, one of the things that makes this super simple is the fact that I do know the y-intercept right off the bat, right? When x is 0, I can see that y is 6. So my y-intercept is at 6. And that's going to be the value of b that I use. Remember, the standard equation of a line, or slope-intercept form, is y equals the slope times the value of x plus b, the y-intercept. Well, I already know b is equal to 6. The next thing that I need to do is find the slope. And slope is change in my y's, right? I can write this as how do y's change over the change in my x values. And if I look at, y values, I'm going to go from 0 to 6. So I have 0, 0 minus 6 in my numerator, and I'm going to have 2 minus 0 in my denominator. So my slope is a negative 6 over 2, which is equal to negative 3. So my slope is negative 3. Now because I know these two values, I can write the equation of this line. It is y equals negative 3x plus a 6. Now if I didn't know right off the bat what my y-intercept was, what I typically would do is I would write this equation, y equals mx plus b. I would write the slope value that I found, negative 3, and then I would pick one of my 2 points, the x and y points. So like if I pick the 0, 6 point, I would put a 6 here, and then I would put my value of x here, and then I would solve for b. Well, you can see that's pretty easy to solve for b in this case because this is just equal to 0. But I just wanted you to be aware of the fact that just because you don't know what the y-intercept is off the bat doesn't mean you can't find it. You just need to plug in one of the points that you have, the x value and the y value from that point, and plug in the value of the slope that you've found. At that point, the only variable that you have left is the y-intercept, and you can solve for that. Part B of this question says, is the point 13, negative 33 on this line? Question is, is it on the line? Look, I don't care. Don't say, yeah, I graphed it. It looks like it's on the line, or my calculator says it's on the line, right? The reason why this can be on the line is if that point makes this equation, y equals negative 3x plus 6, true. If it makes it true, then it's on it. If it doesn't make it true, it's not. So what I'm going to do is I'm going to plug things into this. For example, I can see that, and I'll use this orange color for it, negative 33 is y. So on this side I'm going to write negative 33. On the other side, I can see that b, or x rather, is 13. So I'm going to go ahead and write negative 3, and then I'm going to multiply that times 13. And I'm going to add to that 6. Well, negative 3 times 13 is negative 39. And negative 39 plus 6 is exactly negative 33. So this point is most definitely on the line because when I plug in negative 33 for y and 13 for x, I get the same thing on the left-hand side and the right-hand side of this equation. So 13, negative 33 most definitely is a point on that line. So I guess I should write that. I should say yes, exclamation mark, 13 comma negative 33 is on the line. Why? Because it makes the equation of the line true. So solve for x. I've got 9 to the second power equals 3 raised to the 2x plus 1 power. One of the things that we did was worked on getting things so we had the same base. So if I consider this number 9 right here, 9 is the same thing as 3 getting squared. So I can rewrite this. This equation is 3 getting squared, that is 9, and then I'm going to square that. You can see right here I'm squaring the 9. So inside the parentheses I have 9, and then I'm squaring it. Now if I was to simplify that, 3 squared squared, that's equivalent to 3 to the 4th power. There's 2 factors of 3 squared. 3 squared, 3 squared, 4 factors of 3, 3 to the 4th. Now that equals, on the other side, 3 raised to the 2x plus 1. The only way that these two quantities can be equal to each other, because they have the same base, is if their exponents are equal to each other. So that's the technique we've discussed this year. Now that I've got bases that are exactly the same, I can say, let's let 4 equal 2x plus 1. If those are equal, then the original numbers are equal. So I'm just going to make the exponents equal. I'll subtract 1. I get that 3 is 2x, and then we divide both sides by 2, and I get that x is equal to 3 halves. So x is 3 halves. Graph and shade the solution region for the system of inequalities below. Give 3 solutions to the system that have, I don't know where the v went, that have integer values for both x and y appearing off screen. So let's take a look at this. The first one is y's are greater than, and because it's greater than, it's not going to be a solid line, it's going to be a dashed line. I have a y-intercept that's happening at 7 and a slope of -1/2. So I'm going to do this first part in red. So you'll see this in red. I'm going to use a pretty fine pen. But right here at 7 is my y-intercept. And then I'm going to go down 1 and over 2, and down 1 and over 2. And I'm going to go down 1 and over 2. So quickly we've got a pretty good idea what's going on here. And again, we said that this is going to have to be a dashed line. So I'm going to go ahead and just draw the dashed line that goes through here. And the last thing I want to note is that it is y's are things that are greater than this line. So I'm going to shade above that line. The next one I'll go ahead and do in green. It says y's are less than or equal to 1/3 x plus 3. So here is the plus 3. My y-intercept is at 3. This is going to be a solid line because it is less than or equal to. And I'm going to go up 1 and over 3, and up 1 and over 3. And I'm going to go up 1 and over 1, 2, 3. So we've got a great idea of what this looks like. Same exact thing. I'm going to go ahead and draw a solid line right there. And y's are those things that are less than that curve, so I'm going to just shade below that. And then finally, and I'll use orange for this, y's are greater than x minus 5. So here's my y-intercept this time is at -5. And I'm going to go up 1 over 1 and up 1 over 1. So pretty simple slope pattern to follow here. I just continue in this direction. And let me go ahead and grab the ruler again. And this one should be a dashed line as well. So I'm going to go ahead and draw a dashed line here. And here's my region, right? My region, well, because this one is above that line. So if I'm looking at below the green line, above the yellow or orange line, and above the red line, this is my region. All of my solutions live in here. And I just need to give some points that are in that region, and I'll just highlight one of them with blue. So for example, it looks like 9, 4. 9, 4 right there, right? X is 9 and y is 4 would be a point. So it says list 3 of them. That's an example of one, and you can see there's at least 2 other integer values, or points with integer values inside of there you can select. Unfortunately, this question on the test, I left off the 2 points, so you were unable to do this during the team test. But I have the points here for you, and it says write an exponential function of the form y equals ab to the x that contains these 2 given points. I probably, because of the distance between the x values and these points, I'm probably going to go ahead and choose to write this as a system. So this is one approach you can take. You can certainly use a table, and you can do this other ways, but this is the approach I'm going to take. I'm going to start by writing just my general equation, right? Y equals ab to the x. I've written this down here. It's essentially what I'm using. It's written right above it. But what I'm going to do is I'm going to take the x value and the y value that I'm given for each of these points. They both have an x and a y. I'm going to write 2 equations of that form using the given x and y's. So for example, when y is 583.2, that's the y, and then I'll write a, b, and x is 1. So ab to the first power. The other equation I'll write is when y is 2.4, that's equal to a, b, and in this case x is the number 6. So you can see here I've got 2 equations now with an a and a b. And one of the approaches that we took was to get a alone in both of these and then use the fact that a is equal to itself to try and solve for b. So if I write this down here, I'm going to go ahead and the first equation is going to become, I'm going to divide both sides by b. So I get 583.2 over b is what a is equal to. In the other equation, I get 2.4 divided by b to the 6th power is what a is equal to. So you can see there's 2 ways of writing a. What I'm going to do is I'm going to set those 2 values of a equal to each other, and I'm going to go ahead and solve for b then. So I literally get I guess I'll write it over here. I get 583.2 over b is equal to 2.4 over b to the 6th power. The best thing I could do with this is, I think, is get rid of the fractional denominator. Get rid of the denominators, right? I'm going to multiply both sides of this by b to the 6th power. That's what I'm going to try. And if I multiply, in fact, I'll put parentheses around it and try and show this. So I'm going to multiply both sides of this by b to the 6th power, to the 6th. Now, if I multiply the left-hand side by b to the 6th, what I get is b to the 6th divided by a b times 583.2. Well, one of my factors of b cancel, and I'm left with 583.2 times b to the 5th power. And then that's going to equal, on the other side, when I multiply both sides by b to the 6th, this side with the b to the 6th of the denominator, it becomes simply 2.4. This is a convenient trick now. I've got all my b's collected together and no fractions at all. The next thing I'm going to do is I'm going to divide both sides by 583.2. This is going to give me that b to the 5th equals 2.4 divided by 583.2. So my last step then is to consult my TI-83 plus calculator, actually TI-84, and take the 5th root of both sides. So if I take the 5th root of b to the 5th, I'll just show this over the thing. If I take the 5th root of b to the 5th, I'm left with just b. And if I take the 5th root of 2.4 divided by 583.2, I actually get the number, well, what I get on my calculator screen is 0.333333. And when I ask it to turn that into a fraction, it confirms my suspicion. It is 1/3. So I get that b is actually equal to 1/3. Now, I'm almost done, except I don't know the value of a, do I? Or do I? I don't know what a is. But I'm pretty close to getting a because I can see that when x was 1, it produced 583.2. So what I need to do is, instead of multiplying by 1/3, I need to divide by 1/3 to go back to the 0 value. Or said another way, I can go ahead and multiply by 3 to go backwards. So if I'm at 583.2 and I multiply that times 3, I get 1,749.6. So a is going to equal 1,749.6. So my function should look like this, right? Y is equal 1,749.6 times b, which is 1/3 raised to the x power. Now, before I leave this, the thing I'm going to do with my calculator is I just want to verify that the two values that I know, right? There are two of them. One of them I'm circling in green, and the other one I'm circling in blue. Certainly, when I enter x is 1, I should get 583.2, and when I enter that x is 6, I should get 2.4. And I'm going to check that off the video. If I'm wrong, I'll probably re-record this video and you'll never know it. If I'm right, well, yeah, I'm right. Anyways, I hope this was helpful. Given that A is at 4, 5 and the midpoint of AB is at 10, 4, find the coordinates of point B. You guys did really well on this question when you took this as a team test. I'm going to go ahead and just do a quick sketch here. So A is at over 4, and then up 1, 2, 3, 4, and 5. So here's A at 4, 5. And the midpoint is at 10, 4. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and I need to go up 4 units. So it's somewhere, in here. This is my midpoint, and it is at 10, 4. And I'll just put a letter M there because it's the midpoint. Well, if this is at the midpoint, that means that somewhere, somewhere here, this line, somewhere over in here, there needs to be the other endpoint. B should be somewhere in this neighborhood. And what I can do is, if I look at this, my x values increase from an x value of 5 to 10. So that just increased by 6 units. So I know that this has to be at 16, over 16. And if I look at y's go from a 5 down to a 4. I'm going to go down 1 more unit. It's going to go down to a 3. So this is what I claim, and most of you seem to get this just fine. The point has to be at 16.3. Once you have an answer, one of the ways you can check it is that the midpoints x and y should be the average of the endpoints x and y's. So for example, if I was to take 4 plus 16 and divide that by 2, that is 20 divided by 2, which is equal to 10, which is what it should have been. And if I do the same thing for the y's at the endpoint, I have, you can see 5 plus 3, which is over 2, which is 8 over 2, which is 4, which is exactly what it should have been. So definitely 16.3 is the other endpoint, or the other point that makes up segment AB. Given the exponential function y equals 12 times 1/3 to the x, create a table of values for the function, a graph of the function, and a situation that could be described by this function. So I'm going to quickly just generate some xy values here. So here's an x and here's a y. And I definitely look, especially with an exponential function, I like to look at 0, 1, 2, 3, we'll maybe stop at 4. Well, when x is 0, if I plug 0 into that function, I get 12 times 1/3 to the 0, which is equivalent to 12 times 1. So when x is 0, y is 12. When x is 1, I have 12 times 1/3, right? 12 times 1/3 is the number 4. And I can see I'm dividing by 3 each time, right? Each time there's a new factor of 1/3. When I jump out to x is 2, that's going to be a 12 times a 1/3 times another 1/3, which will be 4/3. And when x is 3, it's going to be 4/9. And when it's when x is 4, the function will be 4 over 27. So you can see each time what I'm doing is dividing by 3. And once I have a fraction, I'm just putting an extra factor of 3 in my denominator and simplifying. Now what that looks like on the graph is I've got, I'll use this color orange. I definitely have the point at 12, right? 0, 12. And then at 1, we've got the point that's at 4. So at 1, 4. That's a lot. So the 2/3 went away, and we're just left with 1/3. Next, at 2 we have 4/3, which is 1 and 1/3. So at 2 I have 1 and 1/3. You can see this is quickly decaying. Next we have 4/9, which is actually less than a half. So at 3 we're at less than a half. And then 4 is less than a fourth. This thing gets quickly very, very small. And if I was to just grab a pen and try and draw the line that goes through those, the function looks something like this, right? And then of course it gets closer and closer and closer to this to the x-axis, with actually never crossing it, because each time we're just dividing by 3, and it doesn't matter where you start. If you have something you divide by 3, you still have something. Dividing by 3 is not going to get you to 0, but it certainly will get you very close to 0. And in this situation, it doesn't take very long to get very close to 0. Last part here for this exponential web is that you're asked to come up with a situation that could model this problem. And several of you suggested in class, I think some, maybe it was the 3rd period, I can't remember the exact detail, but it was something like someone's going through chemotherapy, and after 1 month of treatment, 2/3 of the cancerous cells are gone, 1/3 remain. So it's like a 66% reduction in the cancerous cells. So, and then after another month, another 1/3 only remains, so another 2/3 goes away. So, and I don't know if you start with like 12 billion tumorous cells or 1,200,000 cells, but I don't know how feasible that is or if that's a good fit. But that's something that I heard. Another thing someone talked about was water evaporating from a pond, or you've got 12 jelly beans, and each day you eat 2/3 of the jelly beans you have. So you go 12 down to 4, down to about 1 1/3, then to less than a half a jelly bean, and less than a fourth of a jelly bean, etc. So something like that you should write out in the situation box so that you can clearly show that you have an idea of what types of physical situations would fit this exponential model.